I'll just comment, looking at the syllabus schedule. We've completed part of Chapter 7. We're going to finish Chapter 7 today. And let's see. Then next week we'll do all of Chapter 8. And I've got a note in here for April 12th. If anybody decides they need to withdraw from the course, then April 12th is your deadline. Okay, so let me get this out of my way, and I'll share. Yeah, it's there. I'm going to share the PowerPoints, and we'll pick up where we left off last week. And there it is. Okay, let's make a slideshow out of that. There we go. Okay, so we had just finished discussing the gas laws. And the last one we encountered was Dalton's law of partial pressures. So now we're going to get into some more, I don't know if you call them theoretical angles, but eventually what we want is to understand why all these laws work. Okay, when we talk about gases, liquids, and solids, there's always an interest in change of state. And simply put, that's just a change from one physical state to another, gas, liquid, solid. Most of the time, substances will progress through gas, liquid, solid, or solid, liquid, gas, but occasionally they will go directly from one to the other. For instance, dry ice is a solid carbon dioxide, and at room temperature, it will sublimate. That means it will go directly from solid to gas. And that's why dry ice is so useful in shipping things through the mail, because you can keep them cold and it won't get wet. Okay, so how are these changes of state accomplished? In order for a substance to change from one state to another, there has to be a transfer of energy, usually in the form of heat. So if you have a solid, for instance, ice, in order for it to go to liquid water, there needs to be the addition of some heat. So energy is required to go from solid to liquid, and from liquid to gas, of course. Similar, steam would be the gas, that would be the solid, and some more heat would be required. And if you wanted to go in reverse, of course, you'd have to extract heat. But we would add heat to ice to make it liquid, and add more heat to make it gas, steam. So what does that imply? That implies that there are forces holding the molecules of each of these phases together, some more strongly than others. The strongest forces, of course, would have to be holding water molecules in a solid form of some kind. And in ice's case, it's a crystal lattice of hexagon, like that. So each one of these would be a water. It would be an oxygen. And then you would have hydrogen here, 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 like that. and then you would have each one of these would have an extra hydrogen, right? So each one would be H2O, but they form this crystal lattice, and the bonds between them are relatively strong. Not as strong, of course, as the bonds holding the molecule together itself. Now we're talking about what we call intermolecular forces, not intra. Intramolecular would be the covalent bonds. Intermolecular would be those holding the water molecules together in the solid. And if you add heat, excuse me, you break those bonds holding the water molecules together and allow them to slide past one another. Then you get water, liquid water. And if you want to separate them further, then you have to add more heat. In fact, a lot more heat to separate them completely from one another. Okay. And these changes of state are physical changes. We're not talking about chemical changes. Now, similar principles may be involved in breaking bonds. You have to add energy. But in this case, we're adding energy to a substance to make it change state, or we're extracting energy to go the other direction. Okay. So, sometimes it's instructive to look at changes of state as sort of a triangle. So if you have a solid up here, well, that's not good. Let me put a solid. Let's put solid down here. And then liquid over here. And then gas up here. Okay? So you can get transitions from solid to liquid, like we did before, ice to water, or you can go from liquid to gas, okay? Or you can go, actually you can go from gas back to solid, or you can go the other direction. You could go this way, or you could go this way, or you could go this way. And each one of those transitions has a name, right? Solid to liquid, of course, is melting. Liquid to gas would be evaporation. Or sometimes we call it vaporization. Okay. Then if you go from gas to solid, we call that deposition. Okay. Now if we go back the other direction, gas to liquid would be condensation. I'll abbreviate it. The gas condenses into a liquid. Then you could go from liquid to solid. We call that freezing. And then you can go from solid to gas. I mentioned that one a little earlier. That's sublimation. Okay, so we've got 6 possible processes with 3 phases. See, 1, 2, 3, yeah, all 6 are there. Now this is the this is the authors of the book. This is their idea of what's happening, but that's a little too busy for me. I think the idea is that the solid is down here and you add energy, go up in energy to get the liquid and go up more energy to get the gas. Okay. And in each process, you think about, are bonds being formed or are bonds being broken? If bonds are being broken, you would go this direction, solid to liquid, liquid to gas. If bonds are being formed, you go back the other direction, gas to liquid, liquid to solid, or gas to solid would also be bonds forming. Sublimation would be bonds broken. Okay, and in each process, you consider, all right, is energy required or is energy you have to put energy in or take energy out in the form of heat in this example. Let's see. I lost my only student. Must have bad connection. All right. So if you have to add energy to break bonds, there you go. I thought so. Broken connection probably. If you have to add energy, then it's endothermic reaction. And I think, let me check my syllabus. I don't want to introduce topics. I don't want to talk about topics that I haven't introduced. And if I need to introduce them, I'll do it now. Let's see. All right, I do need to introduce this topic. When we talk about energy transfers, particularly heat transfers, we need to discuss them in terms of what is the system and everything else is surroundings. Okay. So, and when we discuss transfers of energy, in this case in the form of heat, they can be quantified. Like how many joules or how many kilojoules are required, say, per mole or per gram to accomplish this phase change. And it's always in terms of the system, the sign of the number. Say it takes 4.18. How about that? 4.18 joules. Joules per gram to accomplish, to break the bonds. This would be, if you're going to break bonds, you add that energy to the system. And that would make the sign positive because the system is gaining energy. That's a positive value. If we have to extract energy to change, say, from a liquid to a solid, then the sign would be negative. Okay? So if you have any value associated with a process, if the energy is being added to the system, it's a positive value. If it's being extracted from the system, it's a negative value. Okay. So let's see. I'll leave that there for now. So if energy is being absorbed or added to the system, that's called endothermic. Endo is the Greek prefix that means into heat. So heat is being added into the system. the other way around. If it's this one, where energy is being extracted, then it's exothermic. Exo meaning out of, as in exit the building. Exothermic. All right, what processes require addition of energy to the system? You have to break bonds. So melting would be an endothermic process. Evaporation would be an endothermic process. Sublimation would be endothermic. Each one of those require energy that to be added to the system. Now, sometimes the system is defined for you, but sometimes you have to decide for yourself what the system is. For instance, if I were to just put a drop of water on my hand, and as the water evaporated, what's required? Energy has to go into the water. So we're saying that the system is that water droplet, and everything else is surroundings, particularly my hand. My hand would be surroundings. So energy is transferred into the water droplet to make it evaporate. And I feel that transfer of energy because my hand gets cool. So energy is being extracted from my hand into the system, which is the water droplet, to accomplish evaporation. Here are the exothermic processes in which heat is removed from the system. Freezing, right? Go from a liquid to a solid. You have to remove energy in order for those interactions to form and hold it in a solid. Or when you condense, go from a gas to a liquid, you're extracting energy. Deposition would also be an exothermic process. Okay, just a reality check here. If heat energy is absorbed into the system, that's an endothermic change of state. If it involves a change of state, these ideas can be used for bona fide chemical reactions also. Right? So don't forget them once we leave changes of state. Don't forget that this is also valuable. Actually, it's standardized understanding of the system surroundings concept, whether it's a physical change or a chemical change, it doesn't matter. It works for both of them. So heat energy absorbed is an endothermic, and exothermic is heat energy is given off. It's extracted from the system. Okay, so I think we're getting into, we're just starting to beat a dead horse here. We've already defined our terms. What is evaporation? Molecules escape from the liquid phase into the gas phase is evaporation. So in order for that to happen, the molecules must gain energy. And some of that energy is initially required to break the bonds that are holding molecules to the surface of a liquid. Right? So your molecules are here, and some of them are leaving into the gas phase. In order to do that, at the minimum, the intermolecular forces must be broken. So if that molecule is right at the surface and you break all those bonds, then it's free. But it's right at the surface, free. Okay? If it needs to go anywhere, it needs a little push. And any extra energy that you supply in excess of that required to break the bond is transferred to that molecule in the form of kinetic energy, speed, velocity. It moves. Right? So you have the energy required to break the bonds potential energy, which is energy that's stored somewhere. So the potential energy is stored in the bonds holding those molecules together. And then whatever is left over is kinetic energy, energy of motion. So that together is the total. Okay? Now, we can speak of evaporation in terms of how fast does it happen, right? That rate of evaporation, and how would you quantify that? Well, you might say the volume of the liquid decreases as you evaporate, obviously. So how fast does that volume decrease? That could be a measure of rate of evaporation. Or you could actually measure, say if it were water, you could measure the relative humidity above that pool. And as the relative humidity increased, then you know that the rate is increasing. There are numerous ways that you can measure it. But in general, the rate of evaporation increases as you add more heat, which means temperature. Right? When we talk about transfer of heat into and out of, the way that happens is there is a temperature difference between the surroundings and the system. Okay, I'm getting off track here. Let's get back to, so if we increase the temperature of the liquid, you increase the rate of evaporation. And if energy is required, then it provides a cooling effect. I used to do research in a greenhouse. One possibility is greenhouse. And in the summer, I mean, even in West Virginia, but definitely where I grew up in Georgia and where I went to graduate school in Louisiana, if you have a greenhouse down there, the summers are going to be extremely hot inside that greenhouse. I mean, it's uncomfortable for me working in there, but it could be deadly for the plants. So you need to keep the temperature cooler for your plants in the greenhouse. And one way we did that, the cheapest way, is by an evaporative cooling system. We had banks of the fiberboard, cardboard panels. And they would sit here on the walls of the greenhouse. And we'd draw air through them. And water would flow down through those panels. And anything that didn't evaporate would fill into a bucket and be pumped back through again. And then you'd have a float system that would automatically replace the water that evaporated. But the fact that that water passed through there and evaporated was, as the liquid changed to gas, it would absorb heat. And that heat would be heat that would have been accumulated inside the greenhouse. That evaporative cooling effect was very effective. Now, there's a trade-off, right? When all that water evaporates, what happens to the relative humidity inside the greenhouse? It goes to 100%, just about, which is not always bad for the plants, but it can be uncomfortable for the people. But it's either that or paying an arm and a leg for air conditioning systems, and that's just not efficient. So let me get back to the topic here. So that's the why. As the liquid evaporates and produces gas, it requires energy and it absorbs energy from its surroundings. Okay, identify whether heat is absorbed or released during the evaporation of a liquid. If the liquid evaporates, are we breaking bonds or are we forming bonds? We're breaking bonds, so that means energy must be absorbed. Heat is absorbed. Okay? Now, we haven't mentioned this earlier, but if you confine a liquid, put it in an enclosed vessel, and initially, all you have in there is liquid and air. Okay? So if you have this vessel, with a stopper in it, and you have a liquid down here, initially there are no molecules of this liquid in the space above it. But depending on what the liquid is, it could happen very quickly, it could happen more slowly. But eventually, you start getting some of those liquid molecules evaporate, right? And they cool the liquid if the vessel's not insulated, then it has unlimited access to energy from the outside. Right? So it really doesn't matter. Let's just say the temperature is constant, and we have a large enough room so that drawing a little bit of energy in here won't change the temperature much. So we have constant temperature. This liquid at that temperature will transition some of its molecules from liquid to gas phase. And as you tend to accumulate more molecules in the gas phase, some of them return to the liquid. Right? They lose energy and they become liquid again. So you start getting return processes. Okay, in the beginning, almost exclusively, the transition is from liquid to gas. But eventually you get enough, since this is closed, you get enough of these molecules in the gas phase that you get a significant number of them start to return to the liquid phase. When that rate of evaporation and condensation is equal, say the rate of evaporation equals the rate of condensation, when that happens, you have equilibrium. You have phase change equilibrium. And it will stay there as long as the temperature doesn't change. If the temperature is constant, then once you reach that equilibrium, it'll stay there. And what you may also be able to measure is if you put a device in here to a gauge, so it can measure the pressure inside there. Instead of 0, you may get a substantial or a measurable pressure. That pressure in there is called the vapor pressure for that particular liquid. And for a given temperature, that vapor pressure is characteristic of the compound that's in the liquid. And let's just say for argument's sake that it's pure. There's only one molecule type in there. It's a pure liquid. That vapor pressure is characteristic of that particular compound at that temperature. Well, I left out a term. It's a physical equilibrium. Right? We can talk about chemical equilibriums for chemical changes also. This is a physical equilibrium. Okay. Now, on the surface, macroscopically, out here, you could initially watch the volume of the liquid decrease as you evaporate more into gas phase. And eventually, it stops. No more loss of liquid volume. At that point, macroscopically, it looks like things are static. Nothing's happening. But on the microscopic level, activity is furious. Evaporation, condensation is happening at a furious rate. It's just that both processes are happening at the same rate. So we don't notice any change. Okay, there's the concept of vapor pressure. And that vapor pressure will depend upon the intermolecular forces, those forces holding the liquid together. If they are weak, the intermolecular forces in the liquid are weak, then at a given temperature, the vapor pressure for that compound will be higher than it would be for another compound that has stronger intermolecular forces. So let me say that in terms of real compounds. Let's see, that needs to walk back a little bit. There we go. Let's say we have diethyl ether. So there's an ethyl, there's an ethyl, so there's two, diethyl, and there's your ether bond, okay? That's a molecule, right? And they don't use it anymore in the operating room, but it used to be an anesthetic. You would put a patient to sleep with ether. Compare that to something even simpler, like a molecule of water. Okay? I'll explain why later, but for now, the intermolecular forces between ether molecules in the liquid are very weak. The forces are very weak holding that liquid together. So when you open the canister of diethyl ether, almost immediately you smell it. This probably wouldn't be a good choice because you can't smell water anyway, but you can smell ether. Let's see if I can pick a different one. I can't think of a good one right now. But if you open a container of water, almost nothing happens. Right? The intermolecular forces holding water molecules together are much, much greater. So the vapor pressure above the surface of water will be very low compared to the vapor pressure above the surface of ether in that enclosed vessel will be much, much higher. Very high pressure compared to water. Okay. You can get even weaker than that, right? The example here is helium. When would you have liquid helium? Not at room temperature, you wouldn't. Liquid helium forms at about 4K temperature, very close to absolute zero. So if you do have liquid helium, then, and you have it in an enclosed container, it better be a strong container or heavily insulated, because that's going to go to gas very easily and form extremely high vapor pressure. Okay. Another term for these compounds that vaporize easily, they're called volatile. Now here we have another ether. This is dimethyl ether. Right? You just chop those off and put an extra hydrogen here. Right? But they're both ethers because of that bond right there. The EPA has standards for measuring VOCs. Whenever someone applies for EPA approval to manufacture a product, if the product has any volatility at all, they have to seek approval from the EPA to meet its requirements for volatile organic compounds. All right? You cannot open a container and produce volatile organic compounds in the vapor phase above a certain level over a certain period of time, and they have standards to go along with that. So those compounds that are in, say, paint thinner, right? You open a can of paint thinner and you can smell it pretty quick. That's unavoidable. But if you have paint, which has a solvent in there, that's it could be organic, right? If you have an oil-based paint, it may have an organic solvent in there to make everything mix together. Then you don't, the EPA won't let you market it if the VOC exceeds the standard. That's why a lot of paints are water-based. They have almost no smell at all. And that's not strictly true. You can smell paint, especially once you roll it on your wall and it starts to evaporate, but it produces those volatile organic compounds at a much lower level than for an oil-based paint. Let's see, I missed, what did I do? Here we go, volatile organic compounds. Okay, so these are volatile substances if they produce a relatively high vapor pressure. And this is qualitative description. Right? Volatile substance, it just means that it's high vapor pressure. We don't say anything about how much. Okay, a liquid in a closed container evaporates for a short time and then condenses as the number of vapor molecules increase. The process is known as physical equilibrium. All right. So when the process of boiling, we didn't mention that one strictly in our triangle. Boiling is a special type of evaporation where the conversion from the liquid state to the vapor state occurs inside the liquid, not at the surface. It occurs inside. And usually, if you're going to boil a liquid, you apply heat from underneath, right? Because heat rises, right? So you give yourself the best chance to absorb as much heat as possible. You put your pot on top of the fire, not under it. So as you add that heat, if there's sufficient heat inside the liquid, then you can form vapor, bubbles of vapor inside the liquid. When that happens, we say the liquid is boiling. for that to happen, the vapor pressure of the liquid now is equal to the atmospheric pressure outside the liquid. Example, the temperature at which water boils at sea level, 1 atmosphere pressure, is 100 degrees Celsius. That's for 1 atmosphere pressure. Now, if you go a mile high, so you go to Denver, I don't know what the atmospheric pressure would be. Probably, let's just speculate. Maybe it's as low as 0.9 atmospheres. It's dropped considerably. May not be that low. Might be only 0.97 or 0.95. But the point is, the temperature at which water boils at that atmosphere is less, right? It may only boil at 95 degrees. Okay? What that means is the amount of energy required to break the bonds and form the vapor is less, because the opposing forces on the surface of the liquid pushing down on the liquid and everything inside the liquid has decreased. So there's an opposing pressure from the atmosphere. And that means you don't need as much energy to raise the vapor pressure to 0.9 atmospheres as you would to raise the vapor pressure to 1 atmosphere inside the liquid. Okay, and on top of Mount Everest, I think the boiling point of water there is like in the low 80s, like 82 or 83 degrees. Okay, so what does that mean in practical terms? Well, if you're going to cook food at higher elevation, it takes longer because you can't get your water any hotter than that. Otherwise, at that temperature, it starts boiling, right? And once you go from liquid to gas by adding heat, the temperature is constant until all the liquid is gone. So if you try to cook and boil an egg in Denver versus Brunswick, Georgia, right on the sea, it's going to take longer in Denver to cook your egg. So your 3-minute egg might be a 4.5-minute egg. So what's the solution to that? Well, the pressure cooker, right? You put your food in the pressure cooker, clamp the lid down, and drop that little weight on top, and the weight is calibrated to establish a certain pressure inside the container. And with the opposing pressure increased inside the container, the temperatures go much higher. That's why you put your canned vegetables in a pressure cooker, because you can get the temperature much higher, and that kills microbes more efficiently than 100 degrees. Okay. So there's a nice picture, green liquid boiling. So the temperature at which water boils, I should say, the temperature at which the vapor pressure of liquid becomes equal to the atmospheric pressure, that is the boiling point. So the boiling point of water in Denver might be 95 degrees, but in Brunswick, Georgia, it would be 100 degrees. So that boiling point is variable. It depends on your elevation or the external pressure. Now, the normal boiling point is established for the liquid at 1 atmosphere pressure, 760 millimeters of mercury, or 760 torr. That's the normal boiling point. Okay. And there are tables of data for each compound that gives you the boiling point at various pressures, external pressures. And I'm sure they're derived from mathematical equations, but it's easier just to look it up in a table. In fact, the vapor pressure of water is dependent upon temperature. So if you need to know what is the vapor pressure, what is the contribution of pressure from water, say we use Dalton's law of partial pressures. The total pressure might be the pressure of a gas that you trapped in a vessel. Right? And you have some reaction here that produces a gas. And it bubbles up like that. Right? And it fills that space. So you trap the gas. Well, what's the vapor pressure of your gas? You have to know what's the vapor pressure of water too, right? Because this is water and it forms a vapor pressure up in that space. So according to Dalton, the total of the two, the gas that you introduce plus the vapor pressure of water, is the total. So you measure the total pressure and then you calculate the pressure of water, vapor pressure of water at that temperature. And there are tables that tell you that. Then you subtract that one from this one and you find out the vapor pressure of your gas. There's a practical application of both vapor pressure and Dalton's law of partial pressures. Oh, I didn't know, I forgot I had this table, right? So here's the boiling point at different elevations. Let's see, Death Valley is going to be a higher boiling point because it's below sea level, right? New York City is roughly sea level, right? So it's 100 degrees. And let's see, 4,000 feet, not quite a mile, Salt Lake City is 96. I got it pretty close. Go up 1,000 feet and you around 95 degrees. That was a lucky guess. Leadville, Colorado is at 2 miles high, right? So the boiling point there is even less. And you go all the way up to Mount Everest. See, I missed that one a long way. 70 degrees at 29,028 feet. That's the boiling point on top of Mount Everest. Okay. I'd be interested to know what's the boiling point of water in outer space where there's no pressure. It's probably the same for all liquids. No, that can't be. Some liquids would remain liquid even in space. Okay, enough of that. So the boiling point of a liquid is defined as the temperature at which vapor pressure of the liquid is equal to the atmospheric pressure exerted on the liquid. What's the vapor pressure of water at 100 degrees C if it's boiling? It's 1 atmosphere, right? So if you measure the barometric pressure at 1 atmosphere, then pure water should boil at exactly 100 degrees Celsius. All right, I mentioned intermolecular forces before. That's as opposed to intramolecular forces. The intramolecular forces are those bonds that are holding the molecule together. And the strongest of those are covalent bonds. The intermolecular forces are those that hold individual molecules together in a given phase. Okay. Okay, I've already said both of these things. These are the forces that hold molecules together, and they are weaker than the intramolecular forces. That stands to reason, is it not? What if you have two water molecules, right? You have the covalent bonds holding the hydrogens and oxygens together. And then you have this intermolecular force that's holding the water molecules together. What if this bond is stronger than that bond? In that case, it would pull that molecule apart, because this one will be attracted. This one will be attracted here by a huge force, and it would be pulling against these that are also being pulled by other molecules. So it would eventually just rip water molecule apart. If this fact were not true, the intermolecular forces are weak compared to the intramolecular forces. That doesn't mean they don't matter, right? They are the reasons for forming the different phases. Now, we have different types of intermolecular forces. The strongest of these are what we call dipole-dipole interactions. Think of dipoles as magnets. You know how a magnet, a bar magnet's like this, and it might be colored at one end here, here. This might be the south end, that might be the north end. Well, if you bring two of those together, like this, that's the north end and this is the south end, you get a strong attraction between those two poles, the opposite poles. For molecules, poles are not strictly speaking magnetic like this is, but they're more electrostatic. In other words, this molecule may have a slight increase in electron density that way, and we generally use a small delta, Greek letter delta, to mean, because this is not a complete charge. It's not transfer of electron from one place to another. It's simply a redistribution of electron density that gives you a slight negative favoring toward that side. That means this side would be a slight positive. Right? Now that forms an electrostatic difference on the molecule. And if you have another molecule that's supposed to be the same molecule, the same compound, what if you have them oriented like this? Then you get an electrostatic attraction. That's the dipole. The dipole is this, and the dipole-dipole interaction is that. Okay? Now, how do those dipoles form? In order for a dipole to form, you need an unequal attraction for electrons across a bond. Right? So if we have, if I draw my hydrogen molecule, right? There's one bond between the hydrogens, And that bond is composed of 2 electrons, right? 1 electron from one hydrogen, 1 from the other, forms that covalent bond. Well, is there unequal attraction for electrons? No, they're both the same atom, so they attract equally. So this molecule has electron density that's focused primarily in the bond, and there's no dipole. So for these types of molecules, you get no dipole-dipole interaction at all. What if we have this molecule, hydrogen fluoride? Okay. Fluorine is the most, and I'm going to use a new word here, the most electronegative atom in the periodic table. It has the strongest attraction for electrons of all the atoms, all the elements in the periodic table. So we tend to accumulate electron density on this side. And that means it's got to come from somewhere. So hydrogen becomes deficient on that side. So that means we have a dipole here. And we use a little arrow with a positive sign on that end. This is the positive side, that's the negative side. That demonstrates a dipole for that bond. And as it turns out, for the whole molecule, because there's only one bond there. So now, if this encounters another HF molecule, and it's oriented properly, like this, we get a strong attraction between them, a dipole-dipole interaction. Okay. Now that can happen with bigger molecules also. Right? You could have, say, ammonia. In this case, nitrogen attracts electrons a little stronger than hydrogens. It's a very small difference. But if you combine them all together, add them together, we call that vector addition, which is, it's not important that you know that or remember it. Combine them all together, you get an overall dipole in that direction. Plus, you've got those electrons up there already. So now when ammonia encounters another ammonia molecule, these positive ends are attracted to that negative end. Now, for this type of molecule and for others, like water, which would be positive down here, negative up here, and for nitrogen, oxygen, sometimes sulfur, but these are the two main ones, you get a dipole interaction called hydrogen bonding. It's the same thing as dipoles, only you have to have a hydrogen bonded to a very electronegative atom like oxygen or nitrogen or sulfur or even fluorine. The hydrogen bond is a dipole-dipole bond, but it's the strongest of the dipoles. That's why water has a very low vapor pressure, because it has very strong intermolecular forces holding it together. And it's because of that hydrogen bond that you get very low vaporization for water. Okay, so that's one type of bond that's available for intermolecular attractions. Oh, by the way, What if this thing comes in here oriented wrong, like that? Fluorine to fluorine, what's it going to do? It's going to repel, right? The only time it's attracted is when it's oriented properly. And that's characteristic of any type of intermolecular interaction. They have to be oriented properly in order for the bonding of any type to work. Okay, so let's say we have, a molecule that has no dipole, for instance, oxygen. There's no dipole there because there's equal attraction both ways. The electron density does not change. It does not permanently change. There's another type of redistribution of electron density that occurs on the microsecond format. It changes and then it reverts. It's only there for just a fraction of a second. So for a fraction of a second, these electrons, which are in constant flux, may temporarily give this molecule a slight redistribution of charge, of electron density. So what is that going to do to a neighboring molecule? Well, this is going to attract electrons. So it tends to draw electrons that way and steal them from this side. So now you have this slight difference and you get an attraction. But it only happens for a split second and then it's gone. These are called London dispersion forces. Dispersion refers to the temporary redistribution of electron density. And London was the scientist who worked on this, is given credit for it. Not the town, it's the person. Okay. So those are the two types of forces that are available for covalently bound molecules. Actually, that's redundant. Any compound that's covalently bound forms molecules, individuals that are independent. If you have ionically bound compounds, then they're not molecules. They form a crystal lattice. And some authors include these interactions, ion-ion interactions and ion-dipole interactions, and I think they're valid to do that. The ion-ion interactions they're not strictly speaking intermolecular forces because ions don't form molecules, but they do hold solids together, and they are forces that must be overcome in order to change a solid to a liquid. In the case of sodium chloride, for instance, the sodium ions attract the chloride ions. Right? And those are full charge differences, plus here, minus there. Those are ion-ion interactions. And of course they're surrounded like that. So you have these forces that have to be overcome, and they're very strong because, and you know they're strong because you have to heat sodium chloride up to well over 1,000 degrees Celsius to make it melt. A lot of energy is required to break those bonds. Suppose you have ions interacting with molecules of dipoles. Perfect example is salt dissolved in water. Okay. So in this container of water, you've got sodium ions. This is water. You got sodium ions and you got chloride ions. Why are they there? There's attraction between the sodium ions and the negative side of the water molecule. You get that attraction. The chlorides are attracted by hydrogens because they're the positive side. Those are ion-dipole interactions, and they typically occur in solutions. Okay, so this is in words, in black and white, what I've already told you. This one is you didn't think you could form a compound between two halogens, right? Fluorine and chlorine, you can. They will form compounds. And there's a difference between the attraction of electrons. Chlorine attracts less strongly than fluorine. So fluorine gets the negative side. This is really, this implies that there's a negative charge there and a positive charge there, but there's not. It's that slight difference in charge, the delta minus and the delta plus. So here you can get hydrogen bonding is a special type of dipole. Hydrogen bound with either fluorine, oxygen, or nitrogen typically. So, and this doesn't have to be small molecules. It can be large molecules. For instance, glucose. And let's see, we get, let's see, down, up, down. And this one can either be up or down. We'll just put it up for this one. So there's an example of a glucose molecule. Each one of these places where you meet, right there, there, and there, those are carbon atoms. We just don't write them in. So notice that you've got oxygen and hydrogen positioned all around this molecule, right? So you have the opportunity for a hydrogen bond between this hydrogen and some other glucose molecule. If this comes close to an oxygen on another glucose molecule, then you'll get the bond. Or if you put this in water, you're going to get instantly this bonding there and this bonding there. That's why, and this is what's known as a sugar. That's the common name for it. It's actually a hexose, which means 6 carbons. 1, 2, 3, 4, 5, 6 carbons, and ose means sugar. So it's a sugar of 6 carbons. But you can have others like sucrose, which is actually it's a disaccharide. Saccharide's another name for sugar. It's glucose and fructose together. But they've all got these extra OHs around them, right? So when you try to put them in solution with water, they form these hydrogen bonds. And that's why you can put a lot of sugar in water. In fact, you can put so much sugar in water that there's hardly any water there because of these very strong intermolecular forces holding the sugar in solution. Okay, so that's hydrogen bonding. All right, why is hydrogen bonding so much stronger than your typical dipole. It's the difference in electronegativity between oxygen and hydrogen, or nitrogen and hydrogen, or fluorine and hydrogen, that makes the distribution of electrons so much broader between the delta plus and the delta minus. That electrostatic difference is where they derive their strength. Plus, with that hydrogen, you have that slight positive charge on the hydrogen. It's concentrated in a very small atom, one proton, right? So that's what's known as charge density. The charge density on a hydrogen is very high. And that charge density is what allows for the extra strength of the bond. It's concentrated in a very small area, volume, I should say. And in addition, I notice here, because it's small, the negative, whatever, the delta negative, can get very close. That space in there is very small. And you know, of course, that the closer you get two charges together, the stronger the attraction. Right? That's Faraday's law. So you get closer, the force of attraction increases as the square of the distance decreases. Right? So if you cut the distance in half, you increase the force by 4 times. And because hydrogen is so small, the negatives can get very close to it, and you get that extremely strong bonding by comparison. Okay, so here's water molecules showing hydrogen bonding, and I've already showed you that, right? There's the negative side oxygen with the positive side hydrogen. Oh, and oxygen also has two lone pairs of electrons. So that adds to the negativity on that side of the molecule. You see them here depicted. There's a lone pair and there's a lone pair. Okay. And this is just a restatement of what I said earlier. Any liquid that can use hydrogen bonding will have a much, much lower vapor pressure than liquids that cannot access hydrogen bonding, simply because the force of attraction is so much stronger. That bond is strong. All right. This diagram illustrates what we call a homologous series. In other words, they're all the same. This one, this one, this one, and that one, except for one thing. We change the central atom. Okay. So if we go from tellurium dihydride to selenium dihydride, and these are in a family, right? A group. Right, so there's your tellurium, selenium, sulfur, oxygen. So they're going to form dihydrides, each one of them, because they're in the chalcogens. They all have 2- charge, and they form these bonds with 2 hydrogens. Now, they're not really they're not ionic bonds. Right? They're covalent bonds. But they're in the same family, so you have 2 hydrogens each. Now, what is the boiling point of each one? That would be a measure of, the boiling point would be a measure of the intermolecular forces. So notice that the boiling point for hydrogen sulfide here is much less than it is for selenium dihydride, or let's see, hydrogen sulfide, hydrogen selenide, or hydrogen telluride. That's not the ski resort, that's the element. Notice that as you go down in the periodic, in that group, then the boiling point increases. Right? So that means that it takes more energy to break the intermolecular bonds with this one, this compound, than it does for this one or for this one. And if we follow the trend, water should be down here. The boiling point of water should be way down there. But it's not. It's way up here. And the only thing that can explain it is hydrogen bonding. These molecules, sulfur has maybe a slight lean toward hydrogen bonding, but it's not significant. And these definitely don't. But since you have access to hydrogen bonding with water, you get a very high boiling point, and that's good for us. If this scenario were true, the surface of the Earth would have no liquid water on it whatsoever. And we would not be able to keep liquid water in our bodies, right? Because at 37 degrees Celsius is body temperature for humans on average. 37 degrees would be right up here. That would be, what, 100 degrees difference? You would boil off all the water in your body instantly. So it's a good thing. Hydrogen bonding for water is very good. All right, these London forces, like I said before, these forces are weak. Let me check my time for a second. So we're good till 11. Look at my hard copy and see. I think we're getting close to. Yeah. We're getting there. I shouldn't go too far over. These are temporary intermolecular forces. Like I said, they only last for a fraction of a second. And they're very weak. But they are for all molecules, they are always there. Even for polar molecules, London forces are still there. The problem is, or the key point is, that London forces are so weak, if you have access to dipole-dipole interactions, then the London forces are insignificant. Right? They only become significant when the dipole-dipole interactions are no longer there. So if you have, you could even have London forces for noble gases, right? If you went from neon to argon to krypton to xenon, we'll stop there. The boiling point as a measure of attraction, the boiling point increases in this direction. Now, we know that there are no, since there's only one atom there, you can't have a dipole. There's no bond, right? So what's holding them together? If the boiling point increases, there has to be an increase in force holding those things together. Now, we're extreme negative Celsius temperatures, right? But it's still an increase. What is the difference as you go down? Size. You increase the size. Now, What does that mean? That means that there's more volume around xenon for these electrons to be temporarily redistributed. And that's what they do. For this big atom, you get London dispersion forces that are substantially greater than krypton, which is greater than argon, which is greater than neon. Okay, so that is and a perfect example of London dispersion forces based upon size. And it's more significant in large atoms and large molecules. Large atoms, obviously. Large molecules also. If the molecule does not have any polar character at all, then London dispersion forces are the only thing that can act. Consequently, if you have, I'm going to introduce another molecule here, hydrocarbon. It has hydrogen and carbon only. That's it. And it's in long chains. Okay. So you can form a homologous series there also. So we start with methane. And then we go to methane, ethane, propane, butane, pentane, hexane, and I'm going to stop at octane. Octane's what's in your gas tank. That's why they call it octane rating. It's named after that compound. So when you buy gas at the station, if you buy a low test, we used to call it, then your octane rating is going to be in the neighborhood of 89. High test, pure octane has a knock factor. It's a pure octane is 100 octane rating. That's the standard. You can get higher than that. In fact, you used to be able to buy gas that was like 105 octane and you use those in high compression engines. Anyway, this series, and as the molecules get bigger, the boiling point increases. So why is that? Well, the molecules are long chains, right? So you have just one there, you have a short one here, you have a little long one there, a longer there, longer there. Whoa, way out there like that. So what does that mean? That means that there's more opportunity for electron density redistribution on a temporary scale. Right? You don't have much room here, much room there, but your increasing room for that movement of electrons gives you access to charge redistribution. That is the basis of London forces. Also, with these long molecules, if they orient themselves parallel like that, you have lots of places along the molecules where you can get interaction. And then, of course, when you get really big molecules like diesel fuel or asphalt, which would be like 20 carbons or 30 carbons, then you start to get physical interactions where the molecules twist around one another. But the key here is that London dispersion forces are always there. It's just, are they significant or are they insignificant? If they're polar interactions, then they're insignificant. They're that weak. But if you don't have access to polar interactions, London forces will do the job. And that's why for things like nitrogen gas. Right? To go to a liquid, you need minus 195 degrees C. You got to get it really cold, because as long as those molecules are moving really fast, they've got too much energy. They overcome London dispersion forces very easily. Right? So they're going to stay a gas for their interactions. You got to get them really cold, slow them down, so they can start to interact with the London forces. Then you can make a liquid out of them. Okay. Oh, here we go. Noble gases, right? You notice that the boiling point increases as we go down through xenon and radon. They're still negative, right? Because they are nonpolar. But there is a trend there. And the trend is associated with the molar mass of each one. So as the molar mass increases, boiling point increases. You can do the same type of thing with the halogens, fluorine, chlorine, bromine. Okay? Fluorine has a boiling point very low. Chlorine has one that's getting there. And then bromine is a liquid at room temperature. Right? Fluorine and chlorine are gases. Bromine's a liquid. Simply because the London dispersion forces are much stronger for the larger molecule here. All right, let's see. I'm getting there. Okay, when we're talking about intermolecular forces in a liquid, which one is the strongest? Hydrogen bonding is the strongest. Now, if you don't have hydrogen bonding as a choice, dipole-dipole would be the strongest. But if hydrogen bonding is there, it is the strongest of the dipole-dipole interactions. So, which are stronger, intramolecular bonds or intermolecular bonds? Intramolecular bonds are stronger, just like I said at the beginning. They have to be. If they're not stronger than intermolecular forces, then the molecules get ripped apart. And that's basically what I'm saying in that statement. Okay, let's look at these. Compares. An understanding of the bonding within molecules in addition to orientation, geometry. So you need to know two things in order to determine if your molecule is polar or not. You need to know, one, polarity of the bonds. Is it there or is it not there? And then you take those polar bonds, if you have them, and you say, what's the geometry? Okay? Before I get to this one example. So there's carbon dioxide. Carbon dioxide. Oxygen is more electronegative than carbon. So each side will be like this. Right? Electronegativity favors oxygen for each side, like that. But when you add these together, they cancel one another out, right? This one's to the positive side, for instance. This one's to the negative side, 0. So overall, the molecule is nonpolar. That takes into account both the polarity of the bond and the geometry. Now, for if the polarity of the bond, or all the bonds, if they're nonpolar, then you don't have to go to the second step. You can't have a polar molecule with nonpolar bonds, right? So that means this one, in our example, is nonpolar. It has no choice. But water is shaped like this. So it has polarity this way and this way. And when you add those together, because it's bent, you add it together, the molecule is polar. So which has the stronger intermolecular forces? What does nitrogen have available? London dispersion forces, that's it. Water has both, but it's also dipole-dipole of a special kind, hydrogen bond. It's very strong. Right, and there's your explanation. Okay, let's see, I'll leave that up there for the next one. We're almost there. Finish chapter 7 today, and then we'll get chapter 8 next week. So if we draw the Lewis dot structures, I think we've done that, haven't we? Lewis dot structures. If we draw the Lewis dot structures for these two molecules, notice that their molecular formulas are identical. C2H6O, right? C2, 1, 2, 3, 4, 5, 6 hydrogens, oxygen. 2 carbons, 1, 2, 3, 4, 5, 6 oxygens, hydrogens, and 1 oxygen. So there you go. It's the same formula, different structure. So what do we know? Well, oxygen for dimethyl ether is going to be pulling like this. Like that and like that. Those arrows are supposed to be equal in length. They cancel one another out. So this is a nonpolar molecule. Whereas ethanol, the drinking kind, is CH3 CH2O H. Right? There you have the potential for hydrogen bonding with other ethanol molecules. So that's why the boiling points for this one is much higher than for this one, because the intermolecular forces for this one are much higher than the intermolecular forces for this one. This one has hydrogen bonding available. This one only has London dispersion forces. All right. We got another one? Looks like we do. Let's see. Oh, good. We're on the last page. 5 slides. Which gas would behave more ideally at the same conditions of pressure and temperature? All right. Now we have to talk about ideal behavior. And we did that last week, but I'll refresh your memory. So, what makes for an ideal gas? An ideal gas is one in which it stays a gas all the way down to absolute zero. Right? And the molecules do not interact. There's no intermolecular interaction. Okay. This one refers to the fact that we treat the molecules of a gas as point volume, as they had no volume. Well, this also refers to the intermolecular forces, because if you have intermolecular forces, then if you get it really cold, then they'll change from a gas to a liquid, or sometimes even to a solid. But this one, no intermolecular interactions, means that they don't attract one another at all. They don't repel, they don't attract, they act like billiard balls when they smack up against each other. So, if these are held at the same temperature and pressure, which one's going to be more ideal? The one that has the least tendency to interact with its neighbors. And that means the one that has the smallest intermolecular forces, if they are available at all. Nitrogen, we said, was London dispersion. How about this one, CO? Yeah. There you have a dipole toward the oxygen. And since there's only one bond, then that's polar molecule. So these intermolecular interactions, ideal behavior is no, right? There's nothing that's that. Nothing has no intermolecular interactions. So ideal behavior is a theoretical. It's hypothetical. It's a postulate. But the weakest of all is nitrogen. Now, when can you weaken those bonds? If you increase the temperature, right? High temperature. And if they're very tenuous, lots of space between the molecules. Right? So what that means is ideal behavior is exhibited most commonly by gases that are low pressure and high temperature. High temperature overcomes any intermolecular forces, and low pressure means that there are very few of them there to interact, and you get ideal behavior. Now, what does that mean? Low pressure, high temperature. Compared to what? Actually, 1 atmosphere is low pressure, or anything less than that. High temperature, standard temperature. That'd be pressure. Standard temperature would be 0 degrees for gases, 25 degrees for all chemical reactions. So under those conditions, compared to what? Compared to absolute zero, right? Zero is 273 K. That's high temperature. So, like it is now, comfortable for me, this is high temperature, low pressure. So gases measured under these conditions should behave ideally. And in fact, it was fortunate that that's true, because when the original investigators of the 17th and 18th century started looking at gases, they treated gases as if it didn't matter what the gas was. And that's because all gases behave alike at high temperature and low pressure. Ideally. Okay. And there it is in black and white. Oh, okay, we are at the end. And I got 3 minutes, I think. 3 minutes? No, I got more than that. So I can take my time. All right, let's make some space here. And get back on screen. There we go. Okay, to hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. When you retrieve them, you're disappointed to find the balloons deflated. As they warm up to room temperature, they return to their original size. What gas law is demonstrated in this scenario? All right, what are we looking at? Volume, right? The volume shrunk. They went from this size to that size inside the freezer. And then when you pulled them out, they came to this size, right? So we got volume. Okay, what else? What else changed? Temperature. Temperature changed. Right? Anything else? Pressure's the same, right? 1 atmosphere pressure all around. Pressure didn't change. How about the number of moles? right? Remember the four factors describing a gas? Pressure, volume, temperature, moles. Moles didn't change because the balloons were tied. Right? So these are the only two that varied. And what law is that? What describes that relationship? Charles' law. I do it like this. Charles is his name. Apostrophe is possessive. I don't know. Between the time I went to school as a grade school, high school, and now, those who think they know have decided that we have to add apostrophe S on everything, even if there's an S already there. It used to be you just add an apostrophe. Anyway, it's Charles' law. Now we know it's either C or D. What's the other part of the question? What happens to the kinetic energy of the helium during the warming process? During the warming process, you're adding heat to your system. That means that the gas molecules are speeding up. Right? Increased velocity, increased kinetic energy. So D would be the answer. Okay? All right, I think we have one more. A gas-water displacement experiment is set up, and it's determined that 0.812 grams of gas displaces 350 milliliters of water. The atmospheric pressure is 750 millimeters of mercury. The temperature of the water is 20 degrees, so the temperature of the gas will also be 20 degrees. And the partial pressure of water is 18 millimeters of mercury. What's the molar mass of the gas using the ideal gas equation and the R value there? All right, let's put what we know. Word problems are meant to confuse. So let's put what we know on the board in some form that will extract the information. What's the mass of the gas? All right, we got that first. It's 0.812 grams. Okay. What is the volume, total volume of the gas? That is the total volume of all the gases. And recognizing, based on what I described earlier in this discussion, that when you trap a gas over water, there is a noticeable vapor pressure. That total pressure is both, excuse me, I wrote that wrong. That's the volume, that's the total volume. So that's okay. Total volume is 350 milliliters. Right? Okay, atmospheric pressure. So piece of B for barometric pressure is 750 millimeters of mercury. And the temperature is 20.0 degrees C. Okay. Oh, we don't even have to look it up. The partial pressure of water is 18 millimeters of mercury. So the partial pressure of water vapor is 18 millimeters of mercury. Okay, what else? Well, we're given the formula and we're given the gas constant. So we don't have to write that one down. All right, how are we going to approach this problem? The question is, right here, determine the molar mass of the gas. Molar mass is what? I write it molecular weight, same thing. Molar mass is mass per moles, unit moles. So we need to know those two values, here and here. We know the mass already right there. So we need to find how many moles of gas do we have trapped over that water. That's displaced water. So we have a volume of 350 milliliters. Right? That's the same whether it's water vapor or our gas. Temperature is the same. Here's the vapor pressure. What's the pressure of the gas? Well, the total pressure inside that container is atmospheric pressure, right? Because it's balancing against external pressure. And we're assuming that the water level inside the container is the same as the water outside, right? If it is, then that's true. The pressure inside is the same as the pressure outside. If there's a difference in water level, like if we move our bottle up or down, then there's a difference based upon the difference in height of the water. We don't want that. So what you do is you move your bottle until the water levels are equal, and then you measure its volume. So the volume inside is that. The pressure, total pressure is 750, but the pressure of the gas is what? The pressure of the gas is equal to 750 minus 18 millimeters of mercury. Okay, which is equal to what? Get out my calculator. I could probably do it in my head, but I like my calculator. 18. 732 millimeters of mercury. Okay? Now, what do we need to know? Pressure, volume, moles, R, and T. Pressure. We got pressure. But we don't have it in the right units, do we? It needs to be atmospheres. So it's 732 divided by 760 is the pressure. How about the volume? 350 milliliters. How many liters is that? 0.350. Okay, number of moles, that's our unknown. And then we have 0.08206. That's the one I remember. They said 0821. That's okay. And then temperature. What's the temperature? 20 plus 273. 293 K. There you go. Now we can solve for moles. We just say this term times that term divided by this term divided by that term, and we have moles. Oops. There's only one equal necessary there. So let's do that calculation. 732 and divide by 760 is, I did it wrong. Let's try it again. 732. 0.963 times 0.350. Right. Then divided by 0.08206, and then divided by 293. So I get 1.402. 1.402 times 10 to the minus 2 moles. Okay. Now we can do the calculation. The molar mass is 0.812 grams divided by 1.402 times 10 to the minus 2 moles equals what? All right, 0.812. I get 57.9. grams per mole. Round it off. Let's see, should I round it off? 3 there. Actually, we should have 3 significant figures, but the closest one to it is 58. Oh, I forgot. I actually worked it out here. Let's see if I did it right. Okay, yeah. There it is, 58 grams per mole. So we used our gas law, and actually we used the universal gas equation, or the ideal gas equation, and Dalton's law of partial pressures, right here, to solve this problem. So that's everything rolled into one ball of wax. Okay, finished with a minute to spare. Any questions? Let's see, I'll stop the share. There we go. Okay, if you have no questions, then we'll next Monday we'll pick it up with chapter 8, and this exam 3 is only on chapter 7 and 8. What is chapter 8? Chapter 8, solutions. We're going to talk about solutions. Okay, I guess we're done for today if you have no questions.